So E is this number that you are going to be using, but what on earth is it? Well, actually, it comes out of a different question, which is this question. What is the derivative of a to the x? A is just any number. So we know that if y is x to the n, then dy by dx is nx to the n minus 1. And hopefully you've watched the video that proves that from first principles. But what if we swap the n and the x round? What if y is n to the power of x? Then what is dy by dx? So this is the question that leads to us discovering or inventing, very important question in mathematical philosophy, E. Okay, so let's have a look at this derivative of a to the x from first principles and see what happens. So we start with our y is a to the x, and then we say what's y plus delta y? That's the height up here, a to the power of x plus delta x, a to the x plus delta x. So delta y is a to the x. Actually, I'm just going to use my rules of indices to write this. Hope you're happy with that. A to the x times a to the delta x minus y, and y is a to the x. Okay, now I got to divide everything. Actually, I'll tell you what, I could pull out my a to the x there, couldn't I? That'd be nice. A to the delta x minus 1. Now I need to divide everything by delta x. So there's my a to the x, and then I get a to the delta x minus 1 over delta x. That looks disgusting, right? Now, first interesting thing. The gradient, this bit here, has got nothing to do with delta x. So in a minute when I take this limit, as delta x goes to 0, that bit can pop out the front, because we're going to allow ourselves to do that. And then I'll just have to look at the limit of this. Now the limit of this is just, I don't know what it's going to be, but it's going to be some number. So already I can see that the derivative of a to the x is going to be a to the x times some yet unknown number, which is quite cool. Okay, let's have a look at this yet unknown number, and this is where the really clever thing comes in. This thing here, someone noticed, Euler I think, that this could be written like this. A to the 0 plus delta x minus a to the 0 all over delta x. And you might be thinking, so what? But look what we have here. Delta y is a to the x plus delta x minus a of x. Let's just write that down over here next to the blue one so we can see. Delta y is a to the x plus delta x minus a to the power of x. That's delta y. So if I divide that by delta x, then I've got delta y by delta x. And then if I take the limit as delta x tends to 0, what I get is this thing goes to be dy by dx. dy by dx being the gradient of the curve at the point x. Now the only difference between these, the blue one and the black one, is that this is a 0. That's the only difference. So in a minute, when I take that limit as delta x goes to 0, what this is going to be is dy by dx, but at a very specific point, not at a general point x anymore, but, not a general point, but the gradient specifically at the point x is 0. That is what that number that we didn't know what it was up here. That's what this is. So I take my limits. I can pull out the a to the x before I take my limit, because a to the x has got nothing to do with delta x, and I get the limits delta x tends to 0 of a to the 0 plus delta x minus a to the 0 all over delta x, which is a to the x multiplied by, and I'm just going to write it in words for now, the gradient of a to the x at x equals 0. So this is stage 1 of our proof. So what it all comes down to is this gradient at x is 0, so on the y-axis of a to the x. I've drawn that here. Here's a to the x, and here the red line, the gradient of that line is equal to the number that goes here in the derivative. Now obviously a can change, and as a changes, that steepness will change. I've drawn it here with quite a big a. I'll just show you what it's like with a shallower a. So, actually this is a steeper a. What am I doing? I'll do a steeper a since I've started. Here's a steeper a. So this is a bigger a. Y is a to the x, but bigger. So bigger, steeper tangent at the point 0, bigger number here, sitting in front. What if we make a smaller instead of bigger? So less steep. Now it's going to be like quite a chilled graph. It's still all going through the same point, obviously, but this one's going up nice and slowly. So this is also y equals a to the x, but a lot shallower, and that gradient now at the point 0, pretty shallow, pretty low. Not a very big number going on at this point. Not a very big gradient of the tangent at x is 0. But what if we take this to a limit? What if we just say, actually I'm going to make a lower and lower and lower and lower and lower. In fact, let's just make it 1. Let's make a equal to 1. Okay, so that would look like this, wouldn't it? Y equals 1 to the x, because that's always 1. That's a pretty stupid example, because obviously the tangent there would be, the gradient there would be 0, and that makes sense, because if we differentiate 1 to the x, that's just 1, and differentiating 1 gives us 0, so this is the 0 there. So why did I do that? Basically, to convince you that what happens is, as I make a bigger and bigger and bigger, so as I move a forward through this beautiful spectrum that I've created here, this beautiful picture, so a is getting bigger. And what happens to the gradient of the function a to the x at the point 0, 1, which is on the y-axis, as a gets bigger, the gradient at x equals 0 gets bigger. Hopefully you can see that from my beautiful sketch. Now, it started off here, the gradient, 0. Grad equals 0. And then as a gets bigger, the gradient gets bigger. And as we go round here, by the time we get up to like 10 to the x, this gradient is really steep. Like massive, like let's call it massive. The gradient is that a technical word? Maybe. Let's use it anyway. Grad is officially massive. So, what Euler said was, pretty sure it was Euler, he said, okay, so if this is happening, then somewhere in between these two, the dark blue one and the purple one, somewhere there must be one, an a to the x, and for that particular one, this one, I'll draw it, y equals a to the x, and it's somewhere in between the dark blue one a to the x and the purple one a to the x, and for this one, that gradient there must equal exactly 1. That must exist, because somehow that gradient starts at 0 and gets bigger and bigger and bigger and bigger. So at some point, for some a, that gradient must be 1, and that value of a is so special that it is going to be called E. And that is what E actually is. So in general, if y is a to the x, then dy by dx is a to the x times some number, which is the gradient of the graph of a to the x at x is 0. And if y is e to the x, then dy by dx is e to the x times the gradient at the point 0, which is 1. So dy by dx is simply e to the x, which means at any point on this graph, at any point, say this is the point 3, this is the point e to the 3, then the steepness of the tangent at that point will also be e to the 3, the gradient, because the gradient is the same as the value of the function at any point on that curve. Let's quickly return to that original question, what is the derivative of a to the x? Now I've written here y equals ln x, which doesn't look like I'm starting in the right place, but it will work out, don't worry. So first thing, obviously you probably already know this, but since e was the natural number to use, natural number to be concerned with or to use when using calculus to look at gradients of a to the x, calculus with exponentials, that's basically what it is. So the inverse function, log to base e of x, is given its own special name, ln, natural logarithm, because it is the natural logarithm by definition. Of all the logarithms, log to base any number, log to base e is the one which is the most natural to use when we're doing anything to do with calculus, and that's why we write it ln. So why have I written y equals ln x? Because I'm going to quickly remind you of the proof that the derivative of ln x is 1 over x. So I'm going to start by taking e to the power of both sides, and e to the power of log to base e, they cancel, e is the opposite, so that'll just give me x. Then I'm going to differentiate the left-hand side using implicit differentiation, which is just the chain rule, and differentiate the right-hand side as well. Then I'm going to divide both sides by e to the y, and then I'm going to replace e to the y with x, which is what it is, and then there's the little proof that the derivative of ln x is 1 over x. So why did I do that? Let's put that there. Now let's go back to what we actually wanted to prove. Y is a to the x. Okay, so log to base a of y is x. Let's change the base to ln. Ln y over ln a equals x. Ln y is x ln a. Let's differentiate both sides with respect to x using implicit differentiation, or the chain rule, same thing on the left hand side. And on the right hand side, ln a is just a number, so when we differentiate x ln a, we just get ln a. And then multiply both sides by y, and then replace y with what it actually is, which is a to the x. And there we have our beautiful proof that the derivative of a to the x is a to the x ln a. And let's see what we used. Well, first of all, we, at this stage here, differentiated e to the x, which means that we knew that if y is, let me rub that out, it means we were using the fact that y equals e to the x, then dy by dx is also e to the x. That's what I used there. Then what did I do? I just divided under and replaced e to the y with x. Didn't do anything else for that proof. Then, in this proof here, I used the fact that if y equals ln x, then dy by dx is 1 over x, which is what I just proved. And other than that, just fiddled around with it. Didn't use anything else. Pretty brilliant. So now you have 3 brilliant, important derivatives. In fact, the most important? Yeah, the most important. If y is e to the x, then dy by dx is e to the x, almost like, well, by definition, really, that's what e is. If y is ln x, then dy by dx is 1 over x, and if y is a to the x, then dy by dx is a to the x ln